Continuing with this two-level predictor, so now you will notice that all of this hardware to the right of this is the same as what we have seen before. And all of the hard work that we have done is actually in trying to predict this right. So all of this branch history table, the pattern history table, and indexing or concatenating this is just to get the correct direction of the branch. Now I just changed this PHD to indicate a 2-bit counter here. So each of this is now a 2-bit counter. Now, how do we understand this hardware with respect to what we just discussed in the previous slide? So in the previous slide here, we have discussed that if we get a 0, we're going to index into the first counter. If we get a 1, we're going to index into the second counter. Now, if we look at this diagram here, there are lots of counters here. There are 32 entries here. So how do we now understand what we have learned in the previous table with respect to this hardware? So for that, we have to now look at this BHD. So this BHD for this current PC is going to result in 01001. So this is going to be the first counter, which is currently saying strongly not taken. So this is exactly same as what we had here. If this was 1, it would have been strongly not taken. But if it is 0, that is also strongly not taken. So we need one more counter for a 0 history. So currently we have 1 as the history and we have indexed into strongly not taken. Now let us change this history to 0. So if we change this history to 0, we are going to concatenate the PC with it, and this will result in 01000, that is this index of the table. So this is going to read out this outcome which is strongly not taken. So similarly, for a different branch, let's say another branch had a different PC. So then we are going to concatenate its history bit to two other, probably two different counters. So that way, we are going to have multiple counters, each of them 2-bit, and a branch is going to index into one of these two counters based on its history. So that is how we have to interpret this hardware. Now you can also write the same diagram in a different way. You can eliminate all those AND gates and the the mux here. We can just indicate the branch history table, indexing of the PC into the BHD, concatenate the PC and the BHD, and index into the pattern history table. Of course, this is going to be shared by different branches or PCs. You would have noticed it because we are only using part of the PC. So if you have a PC which is 0100 as the index bits, something which has 1110 and 1111 would still index into the same branch history table. So therefore, there could be aliasing or what is also called as collision, which of course happens in a cache as well. So that is inevitable, but we hope that there are not too many branches which are aliasing into the same entry in the table. Another way to eliminate this aliasing is to increase the entries in the table, but that is going to add to the hardware cost. So you have to decide between what is a good amount of aliasing to have in addition to what is the hardware cost you are willing to bear. Also, you will notice that a lot of the PhD entries may not actually get utilized because it really depends on this concatenated entry from the PC and the PhD. So only a few of them are actually getting utilized. So we'll use that fact later on. So currently we will now focus on the 2-bit history predictor. So we said that if we have a pattern which depends on two previous entries, so currently we do not have a way of handling this. So we're going to use what is called a 2-bit history. So 2-bit history, and we're also going to use 2-bit counters. So 2-bit counters means it's going to have 4 states: strongly not taken, weakly not taken, strongly taken, and weakly taken. So similar to the one bit history, we go through this, but this may slightly look more complicated than that. So we are going to look at two previous outcomes. That is why it's called two bit history. And the history bit is going to be used to index into one of the four counters. So because we have two bits for the history, we can have four counters now. So earlier we had a one bit history. We were indexing into two counters, counter 1 and counter 2. Each of them themselves were 2-bit counters. Now we have 2 bits of history, so obviously we can index into 4 counters. So that's shown in this table. Let's say you have a history bit which is 0, 0. What this means is the previous 2 times the branch was not taken. So this can also be considered as an initial state. Now these are the 4 counters that we have: prediction 1, 2, 3, and 4. And let us say that these are the initial states of these counters. And as you would have noticed, they're all 2-bit counters. Now, if you have a history bit of 0, 0, this means I'm going to index into the first counter and take whatever is the outcome from that. So that is the prediction, which is strongly not taken. So this is the final prediction, which is not taken. The actual outcome that I'm trying to trace is N and T, N and T. So N and N are done. This is T now. So the actual outcome is taken, which means that the prediction is not correct. And therefore, what I do is go and change this counter's prediction. So if it's strongly not taken and the outcome is taken, I change it to weakly not taken. So at this point, remember that if I had a 1-bit prediction, I would have changed the state from not taken to taken. Since this is a 2-bit prediction, I am changing it from strongly not taken to weakly not taken. Rest of the counters remain same, and I change the history bit from 0, 0 to 0, 1. So 0, 1 indicates that the last outcome was taken, the last history was taken, and the one previous to that was not taken. I repeat, what does 0, 1 mean? It means the history of the branch. When we say history, it is the actual outcome. This is again very similar to the 1-bit prediction that we did. So you look at the last 2 previous actual outcomes and you note that down as the history bits. Now, for the next iteration, when I get 0, 1 as the history, what I will do is index into the second counter, which is strongly not taken. So the prediction is not taken. The actual outcome is also not taken. The prediction is correct, and therefore I do not change the prediction because it is already in the strongly not taken state. Of course, the next thing that I will do is go ahead and change this history bit to 1, 0, and that 1, 0 is coming from here. 1 is the outcome is taken, 2 outcomes before the current outcome, and the one previous to this was not taken, and therefore it is 1, 0. So that will be the new history bits. And at this point, you can pause and then work out the rest of the table yourself and then compare it with what I'm going to explain next. So 1, 0 is the new history. I will index into the third counter now. So this is the first, second, third. So I'll index into the third counter. Third counter is indicating not taken. The actual outcome is also not taken. Therefore, I retain the same state. And remember that the outcome that we are actually tracing is NNT repeated itself. So now, as we don't change the counter, we go ahead and change the history bit next. So what is the history bit going to look like? It is the outcome of the two previous branches. It is not taken and not taken. Therefore, it is 0 and 0. And then you repeat this. I'll not do the rest of the table. Once you repeat this, you will find out that after the initial training, initially it went wrong a few times, but then later on you will see that the same 0 0 pattern, when it appears again, it is going to start predicting it correct. That is because you see that this counter has changed and undergone changes quite a few times, and it is going to start predicting correctly after the few initial iterations. So therefore, this pattern NNT is going to be predicted correctly after the initial training. And you'll also notice one more thing here, that it is easy to implement this history bit. It is simply like a shift register. You keep using these and shifting them. So you have 0 0 initially, and then 0 1 comes in, and then 1 0 comes in, and so on. So it's really like a shift register that's being implemented. And you'll also notice that if a certain pattern does not occur, so for example, a pattern 1 1 never occurs here in this sequence. So those bits are actually wasted. So you don't really have uh, anything for this particular counter. So you're saving this state here, counter number 4, but that is usually used to index only if you have 1 1 as the history bit, but that is never going to occur. So we're actually wasting those counters and the bits for those counters. So let us look at how the hardware looks. So instead of doing 2 history bits, I've just shown 3 history bits here. So we have the same hardware, the PC. We have the branch history table. So I'm looking at 3 history bits, for example. So I'll use 3 bits of history here. I'll use that to concatenate with some bits of the PC. So obviously this is going to make the PHT much larger. So I have 128 entries now in the PHT. And I can use either a 2-bit counter or a 1-bit counter here. So if I use 2-bit counter, it'll look something like this. And then finally the outcome is still 1 bit, which is it is going to tell me whether to take the branch or not to take the branch. So like I said earlier, these counters are shared across branches because you are using only some bits of the PC. Therefore, branch aliasing could occur, and therefore you're using shared counters across branches, and that is going to increase aliasing. So one of the ways to overcome that is to have more entries in the PHT. So if you have just 16 entries, it is likely that 2 of these PCs will index into the same PHT. Whereas if you have more entries in the pattern history table, you'll see that the concatenated index itself is going to be different because you're going to use more bits from the PC. The more number of entries in the PHT, the more number of bits you need to index, and therefore you will take those from the PC. And therefore, there is less chances of colliding if you have more entries in the pattern history table.